Hi all. Recently, Carl Adams from the Flat Earth Institute of Science put out a new video called Einstein's Failure, Weightlessness. I watched his video and I considered what he said very carefully, and eventually I lovingly crafted a comment response which I posted. No. Now, Kyle is what I like to think of as a silly goose, but he is a nice guy. So I thought perhaps I could expand a bit on my comment. That's this video. So take it away, Carl, and
roll VT.
Before I start talking about weightlessness, I want to answer a question a member of our debate board asked me concerning my statement that if Einstein's claim was right, and that the reason things fall is because the Earth is actually accelerating upward, then everything on Earth should weigh the exact same weight.
well, I'm not surprised he asked that, Carl, because I can think of no reason why everything would have to have the exact same weight just because it's experiencing the same acceleration.
Anyway, our debate board member asked me, if F equals ma, then that means a man with a lot of mass should have more force than a baby when moving at the same acceleration.
That's correct. You have two items, different mass with the same acceleration. They will have a different force, a different weight.
How does that work with your claim that if the Earth was accelerating upward, everything on Earth should have the same weight?
A good question, and one that's been much on my mind in recent minutes.
Well, that's a great question. Let's take a look at that. Here we have three different masses: the mass of the man, the mass of the baby, and the mass of the entire Earth. And if the Earth were causing them all to accelerate at the same rate, since they each have different amounts of mass, they would all indeed have different amounts of force.
Well, let's stick some figures in there, Kyle. If we assume that the man's mass is 100 kilograms and the kid's mass is 20 kilograms, well, they're both experiencing the same acceleration of 9.8 meters per second, which means the force, their weight, is 980 newtons for the man and 196 newtons for the child. Easy.
Even though the same force is pushing on all of them. But this force is something different than their weight.
I think there may be a little confusion here, Kyle. We just calculated F equals ma. That's the force in newtons experienced by the man and the child. This is basically the same equation to calculate the weight. W equals mg, the mass times the gravitational acceleration. They both experience the same acceleration. They have differing masses. Multiplying those two values gives you the force they experience, the weight they feel, in newtons.
This force would be going upward, but their weight is something that goes downward.
The man has a mass. That mass is accelerating. That is the force. Through his feet on the floor, he feels a resistance. He feels his weight. The weight is there all the time, but he's only aware of it when something is pressing against him.
In this instance, our weight can be seen as the amount of g-force we feel in a car when the car accelerates.
Well, not strictly speaking, Kyle, but I'm not going to worry about that. The acceleration you're experiencing in that vehicle, if it was 9.8 meters per second, would be the equivalent of the gravitational pull that we receive from Earth. So it's just a convenient convention. But carry on.
Despite all the passengers in the car having different masses.
Yep, all got different masses. The man, the woman, the boy and the little girl.
We all feel the same amount of g-force.
Yes, they're all experiencing the same acceleration as he puts his foot down. Let's say 1g.
Thus, our weight would be the same.
Oh, Kyle, you've gone and let us all down now, haven't you? We'd better have a look at this maths. They're all in one car, accelerating at the same rate, 9.8 meters per second. They all have a different mass. 100 kilograms for the guy, 95 for the lady, 20 for the boy, 15 for the girl. F equals ma, mass times acceleration, which gives you in newtons 980, 931, 196 and 147. That's the weight that they feel. They're not all the same. I can't understand how you can get the same value using that formula.
In order for one person to experience more g-force than another person here, one person would have to be accelerating faster than another person, and that would result in the car braking in two.
Kyle, I think you need to read up a bit about mass versus weight. Yes, if they all had the same mass, then to experience different weights, they'd have to be accelerating at different rates. But that's not the case. They're all accelerating at the same rate, so your car won't brake. But they all have different masses, so they have different weights. They feel a different amount of force.
Man, just think of all those different things on Earth that weigh different amounts, where the Earth would have to be accelerating at a different rate for each one. I hope you see the problem here.
Yes, Carl, I think I see the problem here. Without wishing to appear rude, the problem appears to be that you haven't got the faintest idea what you're talking about. Of course, various objects have various weights, even though they're all in the same environment of 9.8 meters per second acceleration, because they all have different masses.
So in the train car's frame, which is accelerating forward, it's as if there's an additional gravitational field that points backward. So accelerated frames of reference mimic a gravitational field in the opposite direction of the frame's acceleration.
I'm not sure that using a train rather than a car is going to help your understanding here. What do you think?
Oh, I wouldn't know about that, Mr. Sensible. But I do know I love fluffy kitties.
Okay, I think I may need to carry out a review on my subscribers.
That's interesting. Maybe gravity, just like that backward jolt on the train, is an illusion. Doesn't that point of view seem simpler?
No, I'm sorry. It is not simpler, because in order to feel heavier than another object, it would have to be accelerating faster than the other object.
No.
Alright, now let's go talk about weightlessness.
Yes, let's.
If Einstein was right, should the coyote have to worry about the anvil above his head?
Well, that depends. What gravitational field is he in?
Well, Einstein claimed a falling object is weightless because it has no forces acting on it at all.
Well, if it's accelerating and it has mass, it has weight.
So the weight of the anvil would be the mass of the anvil times 0, resulting in a weight of 0.
Well, if you could find yourself truly in an area that's not in any gravitational field whatsoever, then yeah, your mass times 0 will give you a weight of 0. But even in the depths of space, there's going to be an attraction to the nearest galaxy. So you're always going to have some weight, no matter how small it is.
So because astronauts and cosmonauts are in this constant free-fall environment, they don't actually weigh anything at all, but they still have mass.
No, I'm not making this up. That is their claim.
Well, I'd actually say that NASA video is poorly worded because they still technically have weight, but they can't feel it. They feel weightless.
The only thing the coyote has to worry about is the anvil's weight falling on him. Under normal circumstances, that anvil would be difficult to move out of the way, and that would end up crushing him.
What the coyote is actually feeling is the force of a mass that's been accelerated.
But if that anvil was lighter than a feather, there should be nothing to worry about.
If the anvil had the same mass as the feather, then it'd be nothing to worry about. But if a feather was accelerated to tremendous speeds, then actually the force could cause Wile E. Coyote a problem.
Nonetheless, Lucas on our debate board says, hey, that anvil still has a lot of mass. And since it has a lot of mass, it should be really difficult to move.
And Lucas from your debate board is right. The anvil has a lot of mass and inertia.
And similarly, David claims if both were weightless, you would not be able to move a ton with the same amount of energy as you would be able to move an ant. Keeping in mind the relative positions of other objects, you'd need far more energy to move the ton out of position.
And David Villar from your debate board is correct as well, Kyle. If you have a large mass, it will be harder to move than a small mass. And then, once you've got it moving, it will be harder to stop because of inertia, which is something you haven't mentioned at all.
To that I have to say, please remember here, mass by itself does not equal F.
No, but mass times acceleration does equal F. So if you have a ton weight and you want to move it, you want to accelerate it, you're going to have to use a large force. If that's only a small mass, then when you multiply it by the amount of acceleration you want, you'll only need a small force. Hence, it will be harder to move a large mass than a small one.
And since a weightless mass would have no force, it would have no power to resist any force that acted upon it.
You're still wrong, Kyle. Let's take that large mass and place it in a place where there is actually no gravitational forces acting on it. It truly is weightless. You want to push it. As soon as you start to push it, you're accelerating it. It has a mass, therefore it will require a force to move it.
Now let's go take a look at the definition of weight.
Consult a physics reference book.
Weight describes how heavy an object is, and the word heavy describes how difficult it is to move an object.
Kyle, an online thesaurus probably isn't the best place to source this information. Weight equals mass times gravitational acceleration.
So here you guys are claiming a weightless object should be heavy.
No, Kyle, we're describing that an object with a large amount of mass will have a great deal of inertia.
Guys, those are two completely contradictory terms.
And I'm not sure that you really understand what either of them are.
I'm Mike Massimino, and this is how health is different in space. Weights aren't going to work very well in space. You can take an object that weighs 600 pounds and pick it up with one finger because everything's floating, it's weightless. So you want to be pulling against something for a resistive exercise workout, like a spring or something that has some resistance to it, because that works just fine in space, but actual weights won't.
But hey, if you want to disagree with NASA, be my guest. Don't let me stop you. I will applaud you for doing so.
But Carl, we're not disagreeing with NASA. They do have to use resistive gym equipment, things with springs, etc. Because if you were to pick up a weight, there's no up or down. Your muscles aren't working against anything. But if you had two objects up in the ISS, an anvil and a pen, you could swing the pen around your head like that. Wouldn't be a problem. An anvil would be. It would be hard to get going and hard to slow down. You think when you push a car and it's really hard effort to get it rolling, and then if you grab the bumper and try to stop it, it's just as hard to get it to stop. It's the same thing. It has inertia.
So, Einstein says that anvil is weightless, which means it should not be heavy, and should be extremely easy to move.
It hasn't lost its weight. If you sat that anvil on a pair of scales, both of which are dropping out the sky, those scales will read 0. It has the feeling of weightlessness, but it's still there. And I bet you a pound to a penny that Einstein did not forget inertia, unlike you.
However, if the anvil is heavy, then it isn't weightless.
Kyle, I genuinely would recommend that you do some learning about the difference between weight and mass and what inertia is. Astronauts and the objects on the ISS and the ISS itself, none of them are actually weightless. They just experience the feeling of weightlessness. They're still in Earth's gravitational field, about 90% of it, I think. So they still have weight.
Goodbye, Einstein. Thank you all for watching.
So long, farewell, auf Wiedersehen, good night. Until next time, stay sensible.
Shut up and sit down.